Welcome back. This is Quantum Computing Foundation, Chapter 2, Introduction 2. The centre of gravity today is computational complexity, how difficulty scales, why some walls look eternal, and where quantum algorithms punch through. We will open with a short history, then spend most of our time on Big O and complexity classes. In the early 1900s, quantum mechanics itself is born. Planck, Einstein, Bohr, Heisenberg. In 1981, Feynman argues that classical machines cannot efficiently simulate quantum nature, so we should build quantum hardware. In 1985, Deutsch formalizes a universal quantum computer. Across the early to mid-1990s, Deutsch, Jose, Shor, and Grover show algorithmic advantage, and today we live in the NISQ era. Noisy devices and hybrid workflows. Physics ideas became a formal machine, then algorithms with real stakes. Before complexity, a clearer look at the machines we actually have. Building a qubit means holding a fragile quantum state, controlling it precisely, and measuring it before the environment erases it. Superconducting circuits, think IBM, Google, Rigetti, offer fast gates but need cryogenic cold and often shorter coherence. Trapped ions, ion Q and quantin E deliver high fidelity and long coherence, with slower gates. Photonic qubits can run at room temperature with low noise, yet scaling and error correction are hard. Neutral atoms in optical tweezers promise large arrays, with complex control underneath. Every platform is a trade, none is free. That is why we call this the NISQ era. Noisy intermediate scale quantum. Tens to hundreds of qubits, battered by noise and decoherence, limited circuit depth, and still without full error correction. Applications are experimental, so researchers lean into hybrid loops. A classical optimizer proposes parameters. A quantum circuit runs, measurement comes back. The classical side updates. The variational quantum eigensolver, or VQE, targets ground state energies in chemistry. QAOA, the quantum approximate optimization algorithm, attacks combinatorial optimization. Quantum machine learning, or QML, tries to sharpen pattern recognition. These are strategies for noisy hardware, not magic wands. With that stage set, we turn to the main subject, how difficulty scales. Imagine two libraries. One has 10 books, the other has 10,000. Finding a title is not the same job. Computational complexity asks, as the input grows, how does the time or the memory grow with it? That question decides whether a database search finishes in a second, whether a password falls today or in cosmic time, whether a model trains overnight or never. We capture growth with Big O notation. Big O answers a blunt question. If my input doubles, what happens to the runtime? Keep only the dominant term, ignore the small stuff. Watch the families of growth. Constant time never cares about size. That is Big O of 1. Logarithmic barely creeps. That is Big O of log n. Linear grows with the input. That is Big O of n. Quadratic grows with the square. That is Big O of n squared. Exponential doubles again and again. That is Big O of 2 to the n. The further you move toward exponential, the more dangerous the algorithm becomes for large inputs. Constant time is the light switch test. Checking whether a number is even means looking at the last digit. 7, 42, a billion. Each takes one step. That is Big O of 1. Linear time is reading a book, twice the pages, roughly twice the hours. Double the input, double the work. That is Big O of n. Exponential is a rumor. One person knows it. Each day, every knower tells 2 new people. Day 10 is already 1,000. Day 30 is about 1 billion. Add 1 day and the world doubles again. That is Big O of 2 to the n, and it is why some problems look solvable on a whiteboard and impossible on a clock. Put the growth family side by side and the story gets visceral. At small n, everything looks fine. At n equals 30, 2 to the n is already around 1 billion. At n equals 60, you are near 10 to the 18th. A machine doing 1 billion operations per second, that is 10 to the 9th ops per second, would still burn decades on that scale. Now give that machine a pin to crack. 10 digits, about 10 seconds. 20 digits, thousands of years. 30 digits, tens of trillions of years, thousands of times the age of the universe. Exponential is not an academic adjective, it is a security perimeter. That perimeter is why the internet still stands. Multiplying two large primes is easy. Factoring the product is devastatingly hard for classical algorithms. Real RSA moduli can have hundreds of digits. The best classical attacks sit in a regime we casually call billions of years. Your bank transfer leans on that wall. But quantum algorithms do not have to climb the wall the classical way. A classical computer explores possibilities one after another. Even with many cores, each core still walks a single path at a time. A quantum computer uses qubits in superposition, so many amplitudes are lived together. Interference lets wrong answers cancel and right answers reinforce. Entanglement links qubits, so the computation can coordinate across the register. Those three ingredients do not make every problem trivial, but they change which walls are climbable. Shor's algorithm is the dramatic case. Factoring a real RSA key, classical estimates in the billions of years, quantum estimates in hours to days, that is an exponential leap, and it is why post-quantum cryptography is urgent. Grover's algorithm is quieter but broader, searching 1 million unsorted items. Classical about 1 million steps. Grover about 1,000, which is the square root of 1 million. Quadratic, not exponential, yet it applies to unstructured search across databases, AI and optimization. Two different speed-ups, two different reasons quantum computing matters. Complexity theory sorts decidable problems by resources. Class P is the efficiently solvable set. Time grows like a polynomial in the input size, like n to the k, not 2 to the n. Sorting in big O of n log n, shortest paths, primality, matrix multiplication. These are problems you can build practical programs around. Class NP is different. If someone hands you a candidate solution, you can verify it quickly. Finding that solution yourself may still take exponential search. Sudoku makes the contrast obvious. Checking a completed grid is easy. Solving a blank one is a hunt. The traveling salesman problem is the same pattern. Adding the length of a proposed tour is cheap. Searching all orderings is in factorial hell. NP-complete problems are the hardest in NP. If any one of them falls into efficient classical time, the entire NP landscape collapses with it. Every problem in P sits inside NP, because solving quickly already implies verifying quickly. The famous question is whether NP contains problems outside P. If P equals NP, hard search becomes easy, and much of cryptography loses its footing. If P is not equal to NP, what most researchers believe, then some problems stay genuinely hard even when verification is easy. A correct proof either way is a Millennium Prize problem, and it remains open. Above these classes sits P-space, polynomial memory with no time limit. A machine can reuse tape and explore enormous game trees, which is why deep analysis of complex board games lives in that world. Now power the machine with quantum mechanics. The classical probabilistic baseline is BPP. Fast randomized algorithms allowed a small error, suppressed by repetition. EQP is exact quantum polynomial time, correct with certainty. Historically illustrated by Deutsch's problem, BQP is the heart of the subject. Problems a quantum computer can solve quickly with bounded error. Shor, Grover, HL, and quantum simulation live here. Remember the chain. P is contained in BPP, which is contained in BQP, which is contained in P-space. QAOA is the quantum analog of NP. Proofs can be quantum states, checked by a quantum verifier, with the local Hamiltonian problem as the canonical hard example. The open questions are sharp. Is BPP equal to BQP? Does NP sit inside BQP? Is QAOA just NP in disguise? Evidence leans toward quantum advantage. Proof is still unfinished business. A short look ahead. The blockers are familiar. Decoherence, error rates, scalability, cryogenics, and still too few practical killer algorithms. Near term means more qubits and better fidelity. Medium term aims at logical qubits and larger machines. Long term is a new paradigm that complements classical computing. Globally, more than $55 billion have already been invested, with different countries leading in labs, venture, and talent. The market is climbing from about $1 billion toward tens of billions. That is enough future for now. What should stick from Chapter 2 is the complexity story. Big O names how difficulty scales. Exponential hardness protects cryptography until quantum algorithms rewrite the equation. PNP and P-space sort classical difficulty. BQP is the home class for practical quantum speedups. History and hardware only set the stage. Complexity explains the stakes. That is Introduction 2. Next, we go deeper into the mathematical language those machines speak.